I am completely in awe of the objects that nature has built. When it comes to engineering, biology is really the master of that. And if we look at both the beauty and the functionality of the solutions that nature has provided, there's an enormous set of inspirations for young engineers. Now, all of this beautiful functionality is encoded in a linear string of 4 letters. Rather dull alphabet, but when put together, encodes all of this functionality. The technology of chemical synthesis and molecular biology today has gotten to the point where all of these letters can be synthesized in a laboratory right from scratch so that you can actually sit down and type out the sequence of letters that you would be interested in, email it off to a company in Boston or Northern California, and within a few days, literally, you can get your genes or your entire genome, if you want, back in the mail. So one thing we'd love to be able to do, and this is something my laboratory has been working on for the last 15 years or so, is to take renewable resources, trash, for example, there seems to be plenty of that, sunlight, biomass, a lot of good carbon embedded in these materials, and convince microorganisms to eat those materials. And instead of making more microorganisms, which they're really very, very good at, convince them through reprogramming their DNA to make fuels and chemicals for us. But when you think about it, we have this fundamental problem where we have this capability of synthesizing a genome, but we don't know what it is we would write. So if we're going to convert microorganisms that happily divide and maybe make you sick along the way into ones that will make gasoline for you, we have this fundamental problem. We know how to write it out. We know how to insert it into the organisms. We even know how to convince them to read it as their own, but we don't know what sequence of letters will be the music for that new function. So that's where evolution comes in. Evolution is a great algorithm for design and biology. And as we were discussing at lunch today at the Draper Labs, there's actually one design algorithm for all levels of complexity in biology. There is no human engineered system that has the equivalent. Now, humans recognized this a long time ago, just through trial and error and observation, by breeding organisms together over multiple generations and selecting out from the progeny those organisms that would exhibit some features of interest. They recognized that you could go in phenotypic space, that is, in the properties that they exhibited, all over the place. Now we know, much later, that this is due to changes in the DNA code that comes from recombination and mutation. And now we know, with these different technological tools that are available, we know that we can actually practice this same sort of thing at the level of the DNA that humans have been practicing with organisms. So that's what Pim and I have been doing, or at least I've continued to do it over the last 20 years. We play with these molecules in the laboratory, taking DNA from different sources, mutating it, recombining it, and we can now do evolution, practice evolution in a far wilder way than could have been done in the past. Why is this fun? This is fun because all the molecules in biology that exist in 2011, they're a little tiny fraction of the possible molecules that contribute to the survival and fitness of us and the organisms that exist in 2011. But imagine all the other molecules that you can make. That's where the cure to cancer lies, out there. That's where the solution to the energy crisis. There's a lot of really good stuff out there. And that's my sandbox as an engineer. And evolution provides this strategy for going from the green space out into this, of the physically possible.